Hello, this is Group Wolf, and now we are talking about McEliece Cryptosystem. So, what is McEliece Cryptosystem? It is a public key cryptosystem. Public key cryptosystem is actually by using different sets of public key and private key to do the encryption and decryption respectively, so that we can ensure the people who receive only the people we want them to receive can decrypt the message, since the public key and the private key would be different from each other. And also, such crypto systems has error correcting capability because we use some linear codes which can do error correction. So we can, if the data has error during transmission, we can correct it to some degree. And also, McEliece Cryptosystem is a post-quantum cryptography. What that means is that it is less vulnerable to the brute force attack of the fast computation quantum computers. So something like RSA would be very vulnerable to quantum computers because it can guess so many times as a small amount of time. So let's talk about the pros and cons of the McEliece Cryptosystems. In terms of the advantages of McEliece Cryptosystem, it's a fast encryption compared to RSA, since it can encrypt multiple message or multiple data at once because it uses matrix multiplication, so it's faster comparing to RSA, which encrypt the data one by one. And also, we can it is less vulnerable to quantum computer attacks, as I said before, but the cons will be the large public key and private key size because it uses multiple matrix multiplication. So the public key and the private key will be larger in the McEliece Cryptosystem. So let's talk about the working process of the McEliece Cryptosystem. In the key generation, we first need to select a NKT linear code which is able to correct T errors. What that means is that it has a k by n generator matrix. When the message is multiplied by the generator matrix, it generates a n length linear code word, which is within the linear code C, and the message is k length. And so another thing is that we need to select a random invertible matrix S and a random n by n permutation matrix P. Another word is that we need to another thing to note about here is that all of the elements of the matrix will be within a finite field. The size of the finite field will be set by the user, but here we use F19. Also, when we choose let's continue on. After we have chosen the linear code C and the matrix S and P, our public key would be the G hat and T, where G hat would be the multiplication of the matrix S, G, and P, and the private key would be the S, G, and P matrix respectively. Okay, so when it comes to the message encryption, we first need to choose a k-length message row factor M, and then to generate the code word, we first need to multiply the message row factor M to the G hat matrix, like we talked about before in the public key. So after multiplying it, it will generate a n length code word. And then we need to add a n-length error row factor E with a weight T on the code word generated by the multiplication previously to generate the actual n-length encrypted message row factor C. Why we need to add the weight T row factor E to our original encrypted message row factor? Because since we need to ensure that even though some other people gets the message, it can't decrypt it, because when you decrypt it, the message will not be the same because we deliberately add some error to the code word. So when the people we want to send to receive the code word, he need to first multiply the code word by with the inverse of the permutation matrix P on the right to generate the to generate a C hat. And then we need to use the suitable decoding algorithm to turn the C hat into a k-length in should be to turn into a m hat row factor. And after that, finally we need to multiply the m hat to the inverse of the matrix S to obtain the original message. So all of the step is just a matrix multiplication, but the only hard part would be the finding the suitable decoding algorithm to turn C hat into M hat. So in our attempt, we first chose Reed-Solomon code as our linear code talk about in the last page, because since Reed-Solomon code has a simple generator matrix, which is a transpose of the Vandermonde matrix over a certain finite field. In our case, like I said before, we chose F19 as our finite field, and since the Vandermonde matrix would be the transpose of the Vandermonde matrix would be with each column being the coefficient of a polynomial. So it is quite simple. And the second row would be from zero to n minus 1. So and each column and so if you would like to see how the Vandermonde matrix works, you can check it on wiki or some things like that. But in short, since Reed-Solomon code is easy to maneuver, so we chose it here, and also it has error correcting capability, which is matching the McEliece Cryptosystem's requirements. And since two code words in Reed-Solomon code is at least disagreed in n minus k plus 1 position, its distance is like we learned before in our class is n minus k plus 1. So the most error it can correct is n minus k plus 1, because each code we can distinguish each code at if only it has less than or equal to n minus k plus 1 error. So in our attempt, we also chose a decoder which is suitable for the traditional use of the Reed-Solomon code. The name is hard to pronounce, so I don't pronounce it here. But the general principle is like with has written here. Is an equation for solving for finding two polynomials. We can form a Gauss elimination to perform such action, but in general, let me explain the equation. In the left of the equation, the bi will be each element in our code word received, which is c hat in our case, and then ai will be, like I said before, each element in the second row of our generator matrix, which is from 0 to n minus 1. So and what is E0, EI and QI? EI and QI are the coefficients of the error polynomial EX and another polynomial QX. Since the actual message polynomial is actually QX divided by EX, which is a definition in the decoder. So when we find when we do the Gauss elimination, finding the EI and the QI, and we can perform such division to find our message polynomial. The message after that, since our encryption here, we choose the value of NKT to be 732. the message polynomial's degree would be 2 only, because it will have three coefficients, and thus the message will be the length of 3, which is the length of k, like we said before in the last page. So so when we receive some in here, we can also distinguish if the error is correctable or not, because when we do the division of the polynomial, if the remainder is not 0, the remainder is not 0, which means that the error is not distinguishable. So the message polynomial cannot be found. So the message cannot be retrieved. But conversely, if the remainder of the division is 0, which means that we can actually find the exact message polynomial of degree 2. So we can extract its coefficients and form the m hat vector like we've written here. So to find the coefficient, to find the actual message m in the last page, like we said before. So combining such decoder with the process of the previous page, like we said here, so we can obtain the original message through such decryption and decoding. So here's our full presentation. Thank you.